Okay, another Newton's second law problem. Looks like a lot going on here. We've got a mass in the question. Doesn't matter that it's a hockey player and it's a hockey bag, who cares? We've got a mass of 8. It's being pulled forward with a force of 30, frictions backward with a force of 26, and then we're going to do two parts to this. We'll do it in black. I want to know the acceleration, and then once we get the acceleration, eventually I want to know how far it moves. We can't get the d value, we can't finish the question until we have the acceleration. So we're going to start with the forces stuff. Always a free body diagram. Gravity straight down. Again, don't care how big that is. Later on, we'll do some questions where I care about gravity. For now, we don't care yet though, so I'm not bothering with the math. The normal force is straight up. Those two exactly cancel each other out. The question doesn't say anything about this hockey bag trampolining into the sky or falling through the ground, so I know that the normal and gravity have to be the same. We're pushing forward with an F applied, and the question made up a number of 30 for that. Friction's backwards, and the question made up a value of 26 for that. When we set up F net equals ma, it's always the bigger minus the backward. So in this case, again, F applied minus FF equals ma. We know all our numbers but the a. The F applied was the 30. It's fighting this backward force of friction, which was 26. That's equal to, that's equal to 8 times a. 30 minus 26, that's an overall F net of 4, so 4 equals 8a. If we divide both sides by 8, a is 4 over 8, which is the same as 0.5, and that ends up being a number in meters per second squared. That's kind of the new stuff, but then the question has this tag on part. If we pull for 2 seconds, how far will it move? Let's go take a look one more time. T is going to be 2 seconds. Assume it started from rest, that's our V1, and I'm curious about how far, D value. So if we do a little bit of kinematics, the T was 2 seconds. It started from rest. The A was 0.5, that's what we just figured out. And for some reason we're curious about how far it went. In this situation, don't care about V2. That's that 1/2 AT squared equation. This whole first term drops to 0 since V1 was 0. So basically we have D equals 1/2 of 0.5, which is another half, then multiplied by 2 squared. So we've got a lot of halves and 2's in there. You can double check it on a calculator, but basically we've got half of a half, which is a quarter, times 4, which is 1. In 2 seconds, this thing will have moved 1 meter. I'm going to do one more before I pause the video again. This is one of my favorite questions. This is one that gets screwed up more often than it should. The key to this question, we don't even really have to do any math. Think back to what we learned about F net equals ma, about Newton's first law of motion. This question says that the lab cart's moving at a constant speed. Constant speed means the acceleration is 0. If there's an acceleration of 0, if you think about it, F net equals ma. If the a is 0, that means the F net is 0. Practically, what does it mean if the F net equals 0? Well, that means that all the forces have canceled out. So if we think about our free body diagram, gravity down, that reactive normal force, that's supposed to be straight up. It cancels out gravity. It says we're pushing it with a force of 40. If the net force is 0, what does the backward force have to be? The backward force has to cancel out the forward force. So the friction force in this case is the same as what the forward force is. In this case, it's got a value of 40. We didn't have to do all that work. If you ever come across a scenario that says constant speed, you know that the forces have to cancel out. The backward force has to be the same as the forward force. On the grade 12 final exam, I put a multiple choice question that's a lot like this. I give it a whole bunch of numbers. I make up a mass of a cart. I say how many seconds it's pushing for. But really the bottom line is the forward force has to equal the backward force whenever it's moving at a constant speed.